Okay, so we have the basic tools now for being able to do all kinds of first order differential equations. We can separate it, we can do the first order linear, and then in the last lecture we talked about um, exact equations. And so now, for the rest of the differential equations that we're going to try to solve, what we're going to do is we're going to make some sort of substitution to make it look like one of those other three techniques that we just learned. And so that's kind of like how we did, or what we do in Calc 2. The whole idea behind the U substitution is that so we can make our integral look like one of the basic 9 integrals that you guys all learned as antiderivatives. And anything beyond that will require more techniques, like integration by parts is a special technique. But anything that has to do with substitution is to make your problem look like a problem that you had previously solved, or we have techniques to solve for. So that's what we're going to do here. First, the definition. A homogeneous function is a function that satisfies a property where if you replace all the x's and y's with t times x and t times y, then in the end, it'll look just like your original function, except after factoring out some t's, you're going to get t to some power times the original function. So that's what homogeneous function means. Unfortunately, the word homogeneous in other contexts, like in linear algebra, if you're in the linear algebra class, and later on in this class, we'll see homogeneous in a different light, and that's how I know homogeneous functions or homogeneous equations to be. But anyways, that's the name they gave it. So a way to check if a function is homogeneous is to replace the x and y with t times x and t times y, and see if you can make it look like the original function. All right, so the first order differential equation in the form of, that looks like the exact form that we saw, in this differential form, is said to be homogeneous if both coefficient functions, coefficient of dx and dy, the functions m and n are both homogeneous. And if they are, we can substitute. Now there's two possible substitutions to kind of fix this. And a lot of times one of them is going to work way better than the other. One of them is going to be super easy, the other one's super hard to impossible. So you have to kind of choose the right one, and choosing the right one one takes practice, and two, you just choose one. If it works, it works. If not, then after a certain point, you should know when to stop and try the other substitution. So let's do a problem. And I think these examples over here, or these techniques that we're going to learn, we just talk a little bit about what they are and jump to actually doing an example. So here's our first example. We should first check that it is in fact homogeneous. So we could do that by checking check to make sure it's homogeneous. By taking your m and putting tx in for x and ty in for y. So that means this is your m function. And in your m function, you're going to put t times y, and that whole thing is going to be squared, t times y times t times x. And if you can somehow fiddle with this, mainly factoring out a t, so there's a t squared that we can factor out, and then after we factor out the t squared, all we have is y squared plus y times x. And that looks just like the original m function that we had with the t squared factored out. So that's one of them. And the second one, we'll do the same thing, and we will hope that we're going to get a t squared factoring out as well. So we have a minus tx. Now be careful with your parentheses, because the minus sign is acting on the outside, and then the t squared, or the x squared, is going to take whatever is in for x and squaring it. So tx is what we're replacing in for x. And there's no y's here, so we don't need to worry about that. So there's a minus t squared x squared, or, I mean, if we really want to get technical about that, we get t squared times negative x squared, which is what n of x y is equal to. So they match the powers. So this is homogeneous of the same degree, which means now we can do an appropriate substitution. So the substitution, just like a U substitution, will require you to really think about the differential of what you're letting U or V equal, or in this case, we're letting Y equal to something, or X equal to something. So let's try to do one of the substitutions. Let's try to do this Y equal to U times X business. Now, they're all functions or variables. They're all variables. Y is a function of X, and technically U is also a function of X and Y and stuff like that. So when we take the differential, take the derivative essentially, we're going to make sure we keep track of all the dx's, dy's, and du's. And because u and x are both functions, then we have to, they're functions being multiplied, and we're taking the derivative, so we have to use the product rule. So it's the first times the derivative of the second plus the second times the derivative of the first. And here is our differential. Okay? So now we're going to replace everything. It looks like we're going to replace everything with a y and change everything in terms of u's and x's. What does that mean? I want to replace this y, and anything with a y in it will get replaced, right? So our y is equal to u times x. So your actual differential equation here is going to look like u times x squared plus u times x dx. Right, so wherever I saw a y, I'm going to replace the y, and then wherever I see a dx, I'm going to replace that as well. dy, thank you. Wherever I see a dy, I'll replace that with u dx plus x du. And so this thing will look like a differential equation with u's and x's instead of x's and y's. All right, so we got some work to do here, simplifying work. I'll say u, maybe distribute. I don't know if we need to distribute that. But let's try to combine things and work things out. And here we're going to be distributing the x squared. So this is going to be u x squared dx. And then don't forget the negative in your distribution, x cubed du. So it looks like we can combine a couple of things, or maybe not even combine, just cancel. There's a ux squared dx and there's a minus ux squared dx. So it looks like we can get rid of that. And what do we have left? U squared x squared dx minus x cubed du is equal to 0. Okay. Hopefully that was done correctly. Any objections to what happened? Any issues? Did I do something wrong? Yeah. Right here. So I looked at and replaced the u or the y, u times x. And then, so maybe we'll make that clearer. This is a y. Y. Yeah. And then this is your dy. Okay. Now, if you look at the differential equation that we have, it looks manageable now, right? So let's think back to our 3 things that we've learned. We've learned about exact equations, right? So we could try to see if this is an exact equation, but let's go back even farther. We learned about linear differential equations, or what was the first one? Separable. So if we can separate this, it looks like we can. So let's jump on that idea. Yep. Yes. No. No. You do that after you do the substitution, because after the substitution, we're hoping that our new differential equation that we get is going to be a differential equation that we can solve using some of the old techniques. Now, if we're at this point and this looks harder than what we had before, then we may want to use the other substitution. That might work a little bit easier. Okay. All right, separable. So let's put the du. So let's keep the x as the independent variable and let u be the dependent variable. So let's keep the u on the left-hand side, du divided by u squared. If I bring the du over to the right side and then divide by u squared and then do the switch. And so the dx would be on the other side. And I had an x squared. I'm going to divide out a positive, because I had brought that over to the other side, a positive x cubed. So it's x squared divided by x cubed. Is that right? Algebra. All right. So now we'll integrate both sides. And if you say that the integral of this side, of the left-hand side, is ln u squared, so a common mistake here is that when you integrate this, you're going to get ln of u squared. Okay, it's not. It's -2 power, right? So work out the power there. So maybe I should leave this here and say that's wrong. And u to the -2, add 1, divide, so it's -1 over u, right? Equals, now you get the ln. We'll throw the plus c in. But just like u substitution, when you get your answer, in your integral, in terms of u, that's not what our original problem was. So you want to replace the u back. And so u is going to be y over x, right? So let's put that in here. And then we should get our results, negative 1 over y over x. I suppose we could just write that as x over y. Is equal to ln x plus c. So negative x over y equals ln x plus c. And we want to always try to solve for y if we can. So it looks like if we solve for y here, we can divide out by a negative x and then take the reciprocal. So then y will equal to a negative x over ln x plus c. Yeah? Yeah. Yeah, so we want to be careful about solving for, when we solve for y, um, wherever the plus c happens is going to have to stay there. And if there's some sort of simplifying way to get the c on the outside or get the c somewhere else, then that's fine. But doing a replacement of where plus c is not going to give you the correct answer. Just like when we integrated dy dx equals kx or ky, and then we integrated this, we're going to get, you remember what the answer was? E to the k, I forgot, kt, kx plus c, and then we changed this into a times e to the kx. So when you do this, it didn't become e to the kx plus c on the outside. And so keeping track of where your plus c is important, because that's that could give you a different answer and therefore a wrong answer if you put it in the wrong place. Okay, it's a good question. Well, the solution, this is a solution. There's no initial condition, so we'll call this a general solution. And the general solution usually has a parameter or an unknown constant, the plus c business. And so, yeah, that's all you can say. This is your general solution. Now, how we got the general solution is we did a substitution where our differential equation became a separable differential equation. We did a substitution. Right here is our substitution where after the substitution, our differential equation became separable, and then we're able to just solve for the separable differential equation. But our original differential equation needed a substitution for this to work. So I guess in terms of solving for this, this falls under the category of substitution. Okay, any other questions? All right, let's see if we could do another one. I don't know if I have much room here. Oh, plenty of room. Let's see if we could do separable. Oh, I don't know. I don't know if it's a separable differential equation. And what I meant to say is let's do an initial value problem that has an initial condition. So we would need to solve for the C. But first we should check to make sure that this is homogeneous. So let's see. Again, we identify our N and our M, or M and our N. M and N, and see what they look like if we put in a T times X and T times Y. So M, Tx, Ty. So we're going to put a Tx plus Ty e to the Tx or Ty over Tx. Okay. So in the power of e, the t's would cancel, and that's just a y over x. And then down in the base, there's a t that we can factor out. And so this is exactly what m was equal to begin with. We have t to the first on the outside, and so here we have our, what do you call it, homogeneous function. And so we should expect the same degree for the n function. And again, there's only actually there's a y there too. So minus tx e to the ty over tx. Again, in the power of the exponent, the t's would cancel, and then we can bring the t out. Right. It works, right? Because yeah, because this is a ty and tx, and the t's would cancel, and then it would just be a y over x, which is what we have here. That's the same thing we did up here. Okay, so we'll make this substitution. Let's use the same substitution. What was it? Y equals ux. And remember that dy equals u dx plus x du. And so we're going to replace everything here. All the y's with ux's. So the m function has a y in the base and has a y in the exponent. The exponents will cancel. We'll just have u, e to the u there. So that sounds like it's good news. The next one is just going to be an x, e to the ux over x. And then this is the dy that needs to get split up, u dx plus x du. That's supposed to equal to 0. So let's simplify and see if we can put things together. We have an x dx plus ux e to the u dx, because they cancel. And now we have to distribute this. This is a ux e to the u dx. You can see that disappear. And then we have an x squared e to the u du. Okay. And I suppose we should be expecting things to cancel out like this as a good sign, say that we went the right way. And so now that we have only two terms, it looks like it's a separable differential equation again. Yeah. Oh, yeah. All right, so we'll do the same thing. We'll bring the du over to the other side, and then they'll be positive, and then we'll separate. So this is, again, separable. I'll write it out carefully here. X squared e to the u du is equal to x dx. And so this be e to the u du equals 1 over x dx. Is that right? So now let's integrate e to the u and integrate 1 over x. And it'll be taking the ln of both sides. We'll give you your u. And again, the constant, where it stays, is important. It's inside of one of the ln's, so let's keep it inside one of the ln's. I suppose we still need to replace our substitute for u. So this is a y over x. And so y equals x times ln of x plus c. Yeah, and so we have an initial condition, so we can solve for c. When x is equal to 1, y is equal to 0. So let's put that initial condition in. So 0 is equal to 1 times ln of 1 plus c. ln of 1 is 0, right? So 0 equals ln of c. C equals 1. Okay. So that's your constant, and then your final answer. This is your particular solution. Instead of being your general solution now, since we've incorporated our initial condition, we have our particular solution. X times ln of the ln of x plus 1. Okay. Questions? All right. So you guys can mess around when you're doing the homework. See if one of them would work better than the other. If you have time, you can try that out. All right, we're going to move on to another type of differential equation. And this one is called the Bernoulli differential equation. This is still 2.5. Yeah, this whole thing is going to be 2.5. There's 3 techniques that they talk about here, and I think we should be able to cover all of them. So the first one is that homogeneous method. This one would be identifying a Bernoulli equation, and then the third one is going to be, I would call it a linear substitution or something. Well, we'll get there in a minute. All right. A differential equation that almost looks like a linear differential equation. dy dx equals p of x times y equals plus p of x times y equals f of x times y to the n. And n is any real number. This is called a Bernoulli equation. Note when n is equal to 0 and when n is equal to 1, you actually have a linear differential equation. When n is equal to 0, then this is just f of x on the right-hand side. And that's what we know to be our linear differential equations, first order. When n is equal to 1, this is y to the first power, and that y to the first power and this y could kind of merge in together, and so that's also a linear differential equation. So what we're going to be concerned with is when x, or when n is not equal to 0 or 1. So it could be numbers bigger than 1, or it could be numbers that are less than 0. And I suppose it could be fractions also, but that tends to be a little bit more difficult. So the point is that as long as it's not equal to 0 or 1, then we can make a substitution that would make your original Bernoulli differential equation look like a linear differential equation, in which case we can use the integrating factor business to solve for this. All right, example. What should we do? So let's start off with number 16 maybe. And then we'll see if we can do an initial value problem after this. All right, so remember that a Bernoulli differential equation, as long as n is not equal to 0 or 1, is not linear. And you should be able to look at this and say, oh, this is not linear because the y is being taken to the second power. That's the reason why it's not linear. And you see that it almost looks like a linear differential equation except for the y squared. And so when you see something like this, except you have some y to some power on the other side, then you have to treat it like it's a Bernoulli differential equation, and then we'll do the substitution. So in this case, n is equal to 2. And our substitution, according to their suggestion here, is to let u equal y raised to the 1 minus 2 power. By doing this substitution and changing things around, you should be able to come back and rewrite your differential equation, and they're saying that when you do that, it'll look like a linear differential equation. But instead of x and y's, it'll be u and x. So what is this, -1? Right? So I have a y here. What's y equal to? 1 over u, or u to the -1. And I have an x squared. I should figure out what x squared is, or y squared. I should figure out what y squared is equal to. I'll use -2. Right? What else do I need in this differential equation to do the substitution? We need to find dy. Actually, we can do dy dx. So in this particular substitution, we're going to assume that x is an independent variable for both u and y. So we can just say du dx here. Instead of, the other stuff. So this is our substitution. We'll say du dx equal to, what's the derivative of y to the -1 power? Is it ln? No. What is it? Y to the -2 divided by -2, right? Or multiplied by -2. multiply by -1? Do we multiply by -1? Man, how do you take a derivative? Right, bring the power down, base. Yeah. That's what u is equal to. That's how u and y are related. And so we want to keep that relationship between u and y with respect to x. So be careful when you're taking derivatives and you're not doing integrals. And when you're doing integrals, you're not taking derivatives. So you have to make sure you're doing it correctly. Yes? Oh, I guess I'm not quite done yet. So remember when you used to do substitution, you say dy dx equals to something, or you say du equals something. So here, technically, you're taking the differential with respect to x, and so this is still, when you do this, there's still a chain rule. This is dy dx. So you need a dy dx at the end there. In fact, that dy dx is what's going to replace this dy dx. This looks really messy. Let's see what happens. I mean, if we really want to be formal about it, dy dx is equal to negative y squared du dx, right? If I'm just solving for this, since I want to replace that. Did I do that right? So this negative stays negative, and the negative exponent becomes a positive exponent when I bring it to the other side, right? So that would allow me to replace my dy dx with negative y squared du dx, which is what I'll do in this step now. What? Say it again? The power turns positive, but the negative on the outside stays negative. It's all kinds of negative signs flying around. All right. Negative y squared du dx. Yeah, we probably need to. I suppose we should do that now, huh? Yeah. Oh my goodness, yeah. I need, because when you do a u substitution, you need to replace all the y's with a u's, including the dy dx. So I wrote this negative y squared down, but I'm thinking, wow, or somebody was thinking, this should probably be in terms of u. All right, y was equal to 1 over u. Let's just say u to the negative 1 power. Did I? What happened?
How did you learn from like? Oh, you just changed to y.
There's got to be a smoother way of doing this, where everything looks slick. Yeah, I know. That's the other hard part. There's going to be a lot of negatives here when your n is. I think that would be a good thing to do. Negative even. Negative u squared. No, it depends how you think about it. So you can either multiply by negative u squared, or you can divide by negative u to the negative 2. So if we did this correctly, when we get this into normal form, I'm going to multiply this by negative u squared, and hopefully our differential equation will become a regular linear differential equation. So u squared times u to the negative 2. Think about adding the powers. Negative negative is a positive. U squared times u to the negative 1. And then the last term will just be e to the negative, or negative e to the x, and the u's disappear. And now, so if you look at this, instead of a y, you have a u, but now u is, in terms of u and x, this is a first order linear differential equation. First order linear. Well, and then you solve for it.
Oh, what? Oh, wait, can we do the, oh, yeah, that.
Yeah, that thing.
The white.
Yeah. So this is the whole idea behind the substitution, is to make it look like something that we can already solve for. And again, we know 3 things. We know separable differential equations, we know first order linear, and then we know exact equations. Okay, so with these 3 things, we're doing all these substitutions to make it look like one of those. All right, should we solve for this, or? So our integrating factor is going to be mu is e to the integral of the mu, or the p, times dx. So e to the x. All right, so can I skip some steps? So, no. Okay. All right. In a little while, I'm going to start skipping more steps, okay? I mean, I'm already skipping a lot of steps, but the steps that I've been skipping have been algebra. And then so in a while, I'll be skipping some calculus steps too in the future, okay? All right, so we multiply everything by e to the x. And keeping in mind that this is still a u is a function of x, at the end, we'll need to replace it back into y's. And we know that the left-hand side here is going to be a product rule of something, and that something happens to be e to the x times u. Go ahead and take the derivative to make sure that it's going to be this thing up on top. And then we're going to integrate. And the integral of this is going to be u substitution, e to the 2x divided by 2. And then we get a constant on the outside of that. And then we'll divide by e to the x. And you get negative 1/2 e to the just 1x plus, and then you can write this as e to the negative x times c, or c divided by e to the x, it doesn't matter. If we were to stop there, we would look at the c times e to the negative x. That's a transient term. It goes to 0. And all those other things that we've talked about. But we need to replace u back. What was u equal to again? Y to the negative 1. So this is equal to y to the negative 1. And then to get y, you just take the reciprocal. Yeah, or you could put a parentheses and take it to the negative first power, or write it as 1 divided by that. Either one would work. Yeah. Be careful how you simplify. Yeah. Oh, yeah, when we multiplied. We could have skipped all those steps. Okay. All right. I'll try to remember. Yeah. Mhm. So this is a good segue into asking you to make sure you show your work on the exams, right? If I skip steps, right, I would say it out on the video so we know that we're skipping steps. And unfortunately, you guys aren't taking a video of yourselves while you're taking the test, so you actually need to show. And the thing is that if I understand the steps that you skipped and you got, the correct answer, then that's fine. But if I don't understand what you skipped, or if it's something that I know that even I can't do in my head, then you probably pulled out your phone and got a hold of Wolfram Alpha or something, which is not cool. All right. Any questions about this? Not yet? Not until you work on it on your own. I mean, it all looks fun when you're watching somebody else do it. But that's why you got to do it on your own. Let's try to squeeze in another one and before we get to our last substitution here. Let's do number 22. Ooh. All right. We have y to the 1/2 power dy dx plus y to the 3/2 equals to 1. And of course, this is not in the form that we want. It doesn't even look, at this point, it doesn't look like the Bernoulli equation until we actually try to get dy dx by itself. So I would probably want to multiply by y to the negative 1/2 or divide by y to the positive 1/2 so that we will have dy dx. And then if we subtract 1/2 from the power, what are we going to get? Just 1, right? So y to the first. And then y to the negative 1/2. So what I did here, if I were to show my steps, I would multiply this by y to the negative 1/2 power. That would make this into a 1. Yeah. Yeah. That's to make it look like a Bernoulli equation, we want to get dy dx by itself. And then we notice our Bernoulli equation, and then we can identify our n. No. The reason why it's not a first order linear is because the y is being raised to the 1/2 power. And so that makes it not linear. But it's a nice form. It's a Bernoulli form, which we can make it into a linear differential equation. All right, so now we've identified our n. N is equal to negative 1/2. So u is equal to, what is it, y to the 1 minus n? So remember that n is negative 1/2. So you're going to be adding negative numbers here and negative fractions at that. So be careful when you're, there's a lot of room for little mistakes here where you just, you 1 minus negative 1/2. And you think, oh, that's negative 1/2 or positive 1/2. It's 3/2, right? Make sure it's right. Yeah, it's 3/2. Yeah. That's the n. Yeah. And then we would look to replace all the y's. So if we figure out what y is equal to, you would take the 3/2 root, take the 2/3 power, right? That would make the power equal to 1. So y to the 3/2 raised to the 2/3 equals y, and then u raised to the 2/3 equals, well, that's what y is equal to. And that would allow me to replace my y's in here. Speaking of y's, there's still one more thing I have to do, du dx is equal to 3/2 y to the 1/2 dy dx. Derivative? Remember taking derivatives, integrals? For the y, yeah. Well, I need to replace dy dx, so I probably want to solve for that also. So I'll solve for that by saying dy dx is equal to this reciprocal, 2/3, and the reciprocal of y to the 1/2 is y to the negative 1/2. Okay. So this is like logs. What? Oh, I want in terms of dy. I want dy dx by itself. I also want to make sure I change everything into u's. So 2/3. What? Oh. So what I suggest is do this a couple of times, do it with some friends, and see if you can find patterns and then shortcuts. Okay? Because remember, I'm going to be skipping steps later. This is u to the 3/2 times negative 1/2, or 2/3 times negative. So it's negative 1/3, right? Now plug it back in. So dy dx is 2/3 u to the negative 1/3 du dx plus u to the 2/3 is equal to u to the negative 1/3 again, right? Because that's what we have to replace. We have to replace y to the negative 1/2, and which happens to be here. It is, but when you multiply the whole thing by u to the positive 1/3, so so maybe even multiply 3/2 u to the 1/3 positive, distributed, this would just become a du dx, and that's the other whole point. Plus 3/2 u, 1/3 plus 2/3 is 1, is equal to, this is just going to be 3/2 again. So as you're doing these problems, and maybe you're doing it with other people, I want you guys to observe the u substitution that we're making and the changes that need to be done in the substitution, and then finally look at the resulting first order linear differential equation that you get. There are patterns here that you can find. Okay? All right. You can solve for this. E to the 3/2 x or something like that. Yeah. And then there's still the initial value. So I'll put dot, dot, dot in here. And then tongue. I only do it a little bit. Yeah. But again, you can't do that on the test because I don't know what dot, dot, dot is. All right. Well, good luck with working on these assignments. Is there a quiz next time? No. Oh, so next week we would have gotten a handle on a lot of differential equations. I'll give you guys a quiz next week. On Tuesday next week. Chapter 2. Yeah. Kind of. Yeah.
Yeah.